Le séminaire MfPH Next Generation est un événement pour les chercheurs en début de carrière et les modélisateurs juniors et les épidémiologistes travaillant ou intéressés par la modélisation mathématique des maladies infectieuses et d'autres menaces pour la santé publique. First of all, we wish to acknowledge this land on which the Fields Institute operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Premièrement, nous souhaitons reconnaître cette terre sur laquelle l'Institut Fields opère depuis des milliers d'années. C'est la terre traditionnelle des Huron-Wendat, des Sénèques et des Mississaugas. Aujourd'hui, ce lieu de rencontre abrite encore de nombreux peuples autochtones de Turtle Island et nous sommes reconnaissants d'avoir l'opportunité de travailler sur cette terre. Our guest today is Professor Rebecca Tyson. She is a professor of mathematics at the University of British Columbia and president-elect of Canadian Applied Industrial Mathematics Society. Her work lies mainly in the area of application of ordinary and partial differential equations in theoretical ecology, population dynamics, and epidemiology and opinion dynamics. Notre invité aujourd'hui est professeur Rebecca Tyson. Elle est professeure de mathématiques à l'Université de la Colombie-Britannique et président désigné de la Société canadienne de mathématiques appliquées industrielles. Ses travaux portent principalement sur l'application des équations aux dérivés ordinaires et partiels à l'écologie théorique, à la dynamique des populations, à l'épidémiologie et à la dynamique des opinions. Today's talk will be on changing opinion, how they alter epidemics. La présentation d'aujourd'hui sera sur changement des opinions, comment modifie-t-il les épidémies. Professor, thank you very much for accepting our invitation, and you can start your talk.
Thank you, Idris. Thank you very much for that welcome. Et je vous demande pardon, je n'ai rien préparé en français. C'est tout en anglais aujourd'hui. Wow. I spent a year in France and loved giving talks in French, but didn't think of it this time. This is a nice small group, so please feel free to interrupt with questions if you have any during the talk. I don't mind at all and would enjoy interaction. So let me just put this in presentation mode. There we go. Oh, and I'm not sharing my screen. Just a minute, I'm going to share my screen first. Share screen. Okay, and then we'll put this in presentation mode. So on a talk about opinion dynamics, I should have lots of photos of people talking to each other. Or perhaps texting and things like that. But it turns out when I go through my photos, I don't tend to photograph people. I photograph landscapes. So instead, I'm just going to give you a selection of photos from the place where I live. So you can look at that eye candy as we go through the talk. So I'm at UBC Okanagan, which is in Kelowna. There is a UBC Vancouver that everybody knows about. And I'm at the lesser known UBC Okanagan in the interior. And I've been working on questions around opinion dynamics and coupling those to epidemics. Here are some plots of opinion dynamics. I was just grabbing a bunch of plots off Google, showing how opinions have varied in various places on different issues. And I was giving a talk to the China-Canada conference and decided that maybe I shouldn't show plots of opinions on gay marriage and things like that. So I was a little careful, grabbed the ones that we see here. The two we see at the top here, these are issues on which opinions have changed gradually. So the axis on the bottom here is in years. On here, the axis is in decades. So we're familiar with that idea. So opinions on things like gay marriage or whether or not we need to do something about climate. These are opinions that have been changing gradually over time as people their understanding of the issues changes. And sometimes as new generations come along and have a different point of view. But there are also issues where opinions change really quickly. So at the bottom here, we have some opinion polls leading up to the Brexit vote. And on the right here, we have opinion polls in Canada leading up to the 2016 election. So on this Brexit vote, this red line is fairly stable, but the blue and gray ones are varying quite a bit as people change their minds. In the Canadian election, opinions were fairly stable for quite a while, and then all of a sudden something happened and we got some big swings in opinion. So, and the axes here are in days. This one's definitely days, and this one's a longer period of days, but still days. So once you get into time scales like that, now we're in a time scale where the dynamics of opinions are operating on the same kind of time scale as the dynamics of disease. And so that's going to, the two are going to work together and could change the shape of the epidemic that you would get if you consider them separately. So I have a few main questions. First of all, I have to understand how to model opinion dynamics. So we asked, how do opinions evolve in a population? And how is the outcome of that evolution altered if different subgroups are more influential, or if there's more or less mixing in the population? You could ask many more questions. These are the ones I'm going to start with. Then once I've figured out how to model opinion dynamics, I want to couple this to disease dynamics and see what happens. So how do opinion dynamics alter the time course of an epidemic? And how is the outcome altered if the opinion dynamics are faster than the disease dynamics, or if the population is polarized, which was a real issue in the COVID pandemic toward the end? It's not over, but in the later stages. Okay, so a brief outline. First, I'm going to introduce some background material. Turns out the basis for a lot of opinion dynamics modeling is what's called voter models. And then I'll move into the research I've been doing, which is a model for opinion dynamics, and then a model coupling opinion and disease dynamics. And Idris, I haven't got the chat open. Wait, maybe, can I figure out how to, wait. So if anybody puts a question in there, I can see it. Okay, now I've got the chat. So I can see that. And if I get the participant list, then I should be able to see if somebody sticks a hand up, right? Participants. Okay, so hopefully if you put a hand up, I'll notice. But if I don't, Idris, please feel free to interrupt.
Okay.
Okay, so voter models. That's where we're going to start. These are very simple models. You have a grid. There are two colors of opinions. There's a purple and a red. And people can be either purple or red. And the way opinions evolve in the population is that an individual, say the red one, selects a neighbor at random, looks at that neighbor's opinion, and adopts it. So this red is going to become purple. There we go. And then we repeat. Another individual chooses a neighbor at random. This time the opinions are the same, so the update doesn't look like anything, etc. This time there will be an update. This is a very, very simple model. And so you can think of modifications that might be a little more realistic. One of the simple modifications is the threshold voter model, where now instead of just choosing one neighbor at random, this focal individual looks at everybody in the immediate neighborhood and counts the red votes. There are 3. Was this similar to infecting? That's a good question. Is it similar to infecting? Certainly you could build an agent-based model like that. In infecting, you usually have a probability of, so if we back up, it's a good question. So in infection, you would usually say, if the reds are sick, that the red one will infect the purple one with a certain probability. So that would be a modification of the basic voter model, which you could certainly do.
Well, but here the probability should be 50-50. Maybe I am impressed by the opinion and adopting it, or I reject it.
Right, right. So there are lots of modifications. The basic voter model is pretty stupid. I agree. It just serves as a starting point. So already we have one notion of ways that you can modify it. And can a given node change opinion even if there's no other opinion neighbor? You'd have to do it on a torus, or you'd have some rule for edges. No, probably on an edge. Yeah, I don't know. You do it either way. Either you do it on a periodic domain of some sort, or you'd have a rule around edges where your neighborhood's smaller. So you make the domain big enough so that the edge effects aren't important. Okay, thank you. So another possible modification is this threshold model, where the focal individual counts up the red votes, there are 3, counts up the purple votes, there are 5, and goes with the majority. So red is going to become purple in this case. Now it's departing from infection. This is a bit different. There's the update. The reds become purple. Now, if the votes were counted and there were 4 of each, there'd be no change in opinion because there is now no majority. It's at parity. Okay, so these voter models are really, really simple, but the beauty of them is that you can do some mathematical analysis. So we have a number of results that can be proved, not just with simulation. Excuse me, sorry. Okay. Opinions become clustered in these models. So you start getting spatial groups that are all one color. There's no surface tension in the basic voter model, the really silly one that I said at the beginning, where you pick a neighbor at random and adopt that opinion. There's no surface tension, and the word surface tension came from the physicists, because it's the physicists who developed these models. And so surface tension, an object that has surface tension has some force that resists deformation. These voter models don't have that force. So when you have a cluster of one color, it can be invaded by another color quite easily. Consensus is always achieved on a finite grid and is never achieved on an infinite grid. Though on an infinite grid, the clusters keep getting bigger. So we've already talked about, so I mentioned the threshold voter model. You have suggested 2 other variations, one a more infection type idea where there's some probability of accepting the neighbor's opinion, or you could even have rejecting that neighbor's opinion. You can also do things like consider a larger neighborhood, and you can look at irregular graphs and networks. This work is really interesting. So just the shape of the network can have a strong effect on the clustering, on the surface tension, and on the rate of consensus. One of the things that physicists have been really interested in is, how does polarization develop? So the notion of people talking to each other is that they should move closer together. So if there's mutual understanding going on, then we should be able to see the other person's point of view and shift a little bit that direction, just by virtue of understanding it somewhat. However, in real populations, we see this polarization thing happening. So modelers have added all sorts of other aspects of human opinion behavior. Oh yeah, Schelling segregation model is really important. For those of you who don't know, this is a model where you have a grid and you give people a very slight preference for choosing a home near someone of the same color. Okay, and I'm just talking red and purple and nothing else. Okay, so let's just say that we've got a population randomly distributed, and they go around buying, deciding where to live, but they have a very, very slight preference for a neighborhood that looks the same color as they have. And you end up with the same clustering. You get these segregated neighborhoods. And so it shows that people don't have to be racist in order for these patterns to develop, though there were lots of racist policies that made everything much, much worse. But even without that, these boundaries will develop. Nearest neighbor. I don't know what you mean by nearest neighbor, but you can have nearest neighbor interactions, or you can make that neighborhood larger depending on what you want to look at. Does that answer your question, Itamar?
Yes and no, but you went one step further. But if I'm meeting my neighbors, so my nearest neighbor gets more weight than further, like next neighbor.
Yeah, you can do that too.
So just to continue with the line of thinking of the physicist, there is Ising model for the nearest neighbor that has so much impact. And then people went to the nearest next neighbor and so on and so forth. So, but I think you're taking that in the clustering, the neighborhood, one neighborhood affects the other neighborhood. So that's already generalization of this fine structure nearest neighbor. So maybe the comment should be in parentheses then.
I'm sorry. Yeah, thank you. That's right.
Sure, okay.
Anyway, so there are lots of more complex variations you can add. Individual stubbornness or self-confidence is another way to think of it. Partisanship, that means you pick a color. It's not, you don't care whether it's right or not. You just pick a color because you're on that color team. Heterogeneity, so there can be differences across the population in the way they behave. Social heterogeneity, economic heterogeneity. We saw that was really important in COVID. Some groups wanted to adopt protective measures, but just had far less capacity to do so. And then multiple opinion states. So these are a few examples of more complex variations you could add. Okay, and if you're interested in voter models, there's quite a bit of good reading. These are all in physics journals, not surprising. But some good reading there to get you started. And then I grabbed this from, I think it was Physics Today, excuse me, where they actually showed that the voter model didn't do too badly in terms of figuring out what was going to happen with the US elections, which is not to say, it's not to say that the voter model's right, but it points out that it is actually a useful model as a starting point to understand the system. People are definitely more complex than particles. However, it's surprising how often they behave like particles. Okay, so now let's move into my research. That's the basic background. We started from that, but we're interested in the roles of influence and amplification. So this is getting a little bit into what you were saying, Itamar. So the influence, your neighbors may not all have equal influence. And then there's this process called amplification that I will explain. I want to introduce my collaborators, Bert Baumgartner and Steve Krohn from the University of Idaho. And then two students who worked with us, Noah Marshall and Stephanie Hamilton. They were both undergraduates at the time. They've moved on to bigger and better things. Noah's a PhD student at McGill, and Stephanie finished her master's and is now a private contractor. All right, so I did find some pictures of people in my photo album somewhere. So we're assuming that there are meaningful interactions going on, and we want to model this interaction in more detail. And in our model, as in the voter model, it's one way. So you pick an individual who samples the neighborhood and decides how to change. It's not a bilateral interaction. Okay, so how are we going to model opinions? First of all, we're going to assume that each individual has an opinion from the opinion spectrum, which goes from plus L to all the way to minus L, skipping 0, because 0 causes problems with the model. So you couldn't be entirely neutral in our model. You had to be a little one side or the other. And then given a particular opinion, it's got two parts. So your opinion has a side, which is the sign of A, and it has a strength, which is the magnitude of A. So as you move towards the larger values, your opinion is becoming more entrenched. As you move towards the lower values, your opinion is becoming more moderate. And then updating of opinions in the model depends on influence, amplification, and mixing. Okay, let me explain how we use these. So the influence of opinion A is a function, and it's the likelihood that an opinion of value A affects the opinions of others. And notice this is one way, right? It doesn't matter what the receiver's opinion is. We just had an influence based on the sender's opinion. Okay, so some possibilities. All opinions have the same weight. So uniform influence, we listen to everybody. Or more weight to extreme opinions. We tend to listen to the people at the extremes more than the people in the middle. Or more weight to moderate opinions. We tend to listen to the moderates more than the people at the extremes. So under more weight to extreme opinions, we had linear influence. We also had quadratic influence. And then more weight to moderates, we called these collinear and co-quadratic. And I've shown them here. So the black dots, that's uniform influence. It doesn't matter what level these dots are at. It just matters that they're all at the same level. So they all have the same influence. Here's linear influence. So there's a linear increase as you move across the spectrum toward the extremes. And then here's the quadratic. There's a quadratic increase as you move towards the extremes. Here's collinear. So there's a linear decrease toward the extremes, and co-quadratic. Okay, so that's influence. Amplification. So there's this interesting behavior we have as humans. If you take two people and you put them together in a room, and they start out having opinions on the same side of an issue, doesn't matter how strongly they hold those opinions. That has absolutely no bearing. The outcome is always that they both emerge with more entrenched opinions. So they're holding those opinions more strongly. Doesn't matter where they started, you put two people together who are on the same side, they come out more entrenched. So amplification is the tendency to become more entrenched in one's current opinion when interacting with another individual of the same opinion, regardless of the strength of either opinion. Okay, so what I've illustrated here is a scenario where amplification makes a difference. So what I should have said is we assume that when two people interact, the tendency, so if the individual in this hand picks the individual in that hand, this individual will move towards the partner that was chosen. So that's the basic assumption. Okay, so assuming meaningful interactions where there is understanding going on and mutual respect, there is movement towards the person chosen. Amplification, however, can change that. I don't know what you mean by no convincing and arguing. No, and that usually happens. So when you're on opposite sides, that's when there's more convincing that needs to happen, and that's a whole separate process. Okay, so here's what happens without amplification. So suppose we have our focal individual in purple at +2, and that individual chooses an interaction partner in green who's at +1. So in a normal interaction, the purple would move toward the green. And we assume movement is never more than one step. And so +2 would become +1. If amplification is present, however, notice that these two individuals are both on the plus side of the spectrum. So now the +2 interacting with the +1 becomes a +3 because that individual has had their opinion amplified and is now more entrenched. Now we assume that amplification occurs with some probability. It doesn't always happen. So sometimes you have two people on the same side, but they're not, in a room where they're talking together and getting more and more excited about their opinions. They're having a more engaged conversation where there can be movement towards the focal individual as opposed to towards the extreme. But some of the time, this amplification happens. Okay, so that's the basic framework of the way we modeled opinion dynamics. So now let's look at what happens in a spatial model. So let me introduce my variables. If we've got A sub t at I is the opinion of agent I at time t, and that one's going to be purple. And N is the neighborhood, and then I is the influence exerted by that agent. So here's a bit of pseudocode for time from 1 to the end. We randomly reorder all the people. Well, we don't move them around. We just pick a random ordering of all the people in the grid. And then you go through that ordering from 1 to N. For each individual, you select a neighbor from the neighborhood. But in the basic voter model, you just select a neighbor at random. We select a neighbor weighted by influence. So here's the influence weighting. Each neighbor has an opinion, and that opinion has an influence. And if you sum up all those influences and put that in the denominator, and you put the individual influences in the numerator, you get the weight that each neighbor is given. And then you do a random toss and you figure out which neighbor gets selected. So you don't always select the most influential neighbor, but you're more likely to select the more influential neighbor. Okay, so a neighbor is selected based on an influence weighting. We toss to see if amplification is present. And then we determine the update or the opinion at the next time based on whether or not amplification is present. And where these two opinions lie. And then, so you finish the whole grid, then you update the opinions in the entire grid, and then you start over again. And here's what the simulations look like. So we start with a uniform distribution of opinions. This is a simulation with a spectrum going from -5 to +5. The first thing we see is a centering. So the distribution is mostly towards the middle. But then we start recovering the extremes. And here we have two peaks developing, and you notice the clusters beginning to form. the clusters become bigger and with more sharply defined edges. And now we've got the two peaks are moving out to the extremes, and now they're at the extremes. At this point, we'd call the population polarized. And it remains that way for a very long time if you look at these time indices here. And this pattern in a square grid is extremely stable. So consensus will be achieved on this grid unless you end up with a perfect vertical column. Yeah, but even then, consensus should be achieved eventually, but it can take an awfully long time. So this is the result with amplification at 0.07. So amplification is present 7% of the time. If we look at other levels of amplification, we see the importance of amplification. So if there's no amplification present, that centering is stable. And so all opinions move towards the center. With a little bit of amplification, the opinions move to the center to start, but rapidly start moving towards these extremes, which are in blue and green. These results were obtained with the spectrum from -2 to +2. So the center opinions are -1, +1, and the left and right are -2 and +2. And as amplification is increased, that centering behavior becomes more and more brief and essentially is gone by the time we're up at 0.5 in this smaller spectrum model. The black curve here plots something called Fizz that we invented. So it's tracking the number of positions that change state. And note that when amplification is 0, it remains fairly high, though there is a steady decrease. And in the other scenarios, it's decreasing pretty quickly, which we see here. These edges are becoming more and more defined, sharply defined, and the number of individuals that are actually flipping their or switching, changing opinions is getting smaller. Now, the influence functions do have an effect. So these are two simulations with the same amplification, 5% here. This is the outcome with linear influence, and this is the outcome with collinear influence. So collinear influence, so with amplification, which is this tendency to move towards the extreme when you encounter someone with the same opinion, with an opinion on the same side, then collinear influence, if you listen more to moderates than extremists, can counteract that pretty substantially, not entirely. I mean, we're seeing this slow degradation of the moderate position, but it makes a big difference. And that's just collinear, that's not co-quadratic. So what have we learned from the spatial model? That amplification and influence functions with weight to extreme opinions each lead to polarization, that consensus is slow, and that co-influence, stronger influence by moderates, can counteract the polarizing effect of amplification when amplification is low. And so these are the outcomes from one simple opinion dynamics model where we have made some attempt to include behaviors that are observed in real populations in a meaningful way. So then we want to ask, what happens in the well-mixed case? So this is a spatial model with mixing. I want to get to the disease part of the talk, so I'll go through this a little quickly. So we can have, in this mixing model, we can have local interactions or global interactions. So local interactions, you select from your neighborhood. Global interactions, you randomly select someone from anywhere in the grid. And if there's lots in the way of global interactions, then we end up with an ODE. So if we translate that agent-based model into an ODE, a series of ODEs, one for each group in the population, each opinion, then we end up with equations like this. And so to build these equations, we just count up the number of interactions or the types of interactions that would give us, would make a change to this population. So the -2 opinion group increases whenever a -1 becomes a -2 and decreases whenever a -2 becomes a -1. So these are all the interactions that lead to a -1 becoming a -2. So that's a -1 interacting with a -2, no amplification present, and this weighting is the influence weighting. Or if a -1 interacts with a -1 and amplification is present, you also get a new -2. And here's the influence weighting. So these, those are all the ones that increase the -2 population. The ones that decrease the -2 population, it turns out it's easier to count the ones that don't decrease it, and then the remainder do decrease it. So if a -2 interacts with a -2, there's no change. So that one does not lead to a decrease. If a -2 interacts with a -1, but amplification is present, that also results in no change. So all of the other interactions, that's one, the one here, lead to the -2 becoming a -1. So we take the one and then subtract the ones that don't change it. Okay, and if you go through like that with all of the populations, you end up with a model like this for the -2 to +2 spectrum. We'd like to analyze the model to see if we can understand the behavior that we observed in the spatial model. And we look for the steady states, we find the 2 consensus steady states, and then we find this intermediate steady state where where all of the opinions are still present. However, it turns out all of them are saddle nodes. And so the linear stability analysis is not very helpful in terms of figuring out what's going on. So then we went back to the simulations and we noticed that the 2, so now I've changed colors on you here, but these 2 are the inner opinions. This is +1, this is -1. So the 2 inner opinions are doing the same thing for a while, and the 2 outer opinions are doing the same thing for a while. So that suggests a simplification that we could make to the model to find out what's going on at the beginning. And then out here, the opinions on one side are essentially gone, and the opinions on the other side are dominating. So that's another simplification. Oh, sorry, there was a question back there about randomizing the update order. I've gone way past that. I'm sorry, I missed it. Perhaps we'll come back to it later if there's time. Okay, so if we do those 2 simplifications, this is the first one. We've assumed that the -1 and +1 opinions are both doing the same thing. So we'll call those little x, and the -2 and +2 opinions are doing the same thing, and we'll call those y. And so then you end up with these 2 ODEs, and we can plot the phase plane. We know that these 2 opinions should add up to a half. We're now just modeling half the population. So this line is x + y equals a half. And then the magenta and orange are the null clients, and this dot here is the steady state, which is a saddle. So the initial condition is each of these at a quarter. So that's 0.25, 0.25, so round about here. And if we follow the phase plane, the opinions should move this way. Now, notice that this line, it isn't exactly the stable manifold, it's really close. If there's amplification present, it's not exactly the stable manifold. And of course, in a numerical simulation, you would always end up falling off that line eventually just through noise. So assuming you can't stay on that stable manifold, so opinions are going to move this direction. And notice that that's a centering. The outer opinions are decreasing and the inner opinions are increasing. This is the centering we observe at the beginning. But eventually, because this is a saddle node, there's going to be what I call symmetry breaking, where there's one inner opinion that increases and the other inner opinion that decreases. So at that point, we go to the other simplification. So let's assume we've lost all the opinions on one side and gained opinions on the other side. So now x plus y has to equal 1. So that's what this line is. The steady state is here. And let's assume we went from the first phase plane to this one. So when we left the first phase plane, the outer opinions were near 0. And one inner opinion was increasing rapidly. So we're starting somewhere in here on this dotted or dashed black line, where the inner opinion is large and the outer opinion is low. And then you see from the phase plane that movement is going to be toward consensus on one side at the extreme. So that helps explain what we observe in the spatial model. And when we fit the agent-based model with mixing, put some mixing in the agent-based model to the ODEs, we find a pretty good fit. Okay, so that's opinion dynamics. Now we want to couple opinion dynamics with a disease model. And now opinions have an effect on transmission because we're going to assume that each opinion is associated with a particular type of behavior. So a +2 opinion corresponds to a no prophylaxis behavior. +1, so let's say +2, no prophylaxis, you never wear a mask. +1, you wear a mask most of the time. -1, you wear it some of the time. Sorry, I'm backwards here. Nowhere, so some prophylaxis, that's wearing it some of the time. -1 is wearing it most of the time, and -2 is wearing it all the time. So each of these would have a separate transmission rate. So here are our different opinion groups, and we've put them in the susceptible population. And each opinion group has a different transmission rate based on their behavior. And then we put them all in one infected group and then one recovered group. We haven't tracked opinions in the infected or recovered group. That model was just too big, so we started with just having it in the susceptibles. Okay, so we assume that the transmission rate has a discounting of Q for each increase in prophylaxis level. So beta naught is the baseline infection rate, and Q larger than 1 is a discounting factor. Now we have influence. So influence in this model, we stuck with uniform influence when no disease is present, but then different types of influence as disease prevalence increases. So under this scenario, as disease prevalence increases, the influence of each population is changing linearly with disease prevalence. And this line corresponds to the highest prophylaxis group. And this corresponds to the next down to, and this would be the group that does no prophylaxis. So we're assuming in this model that the always maskers start having more and more influence than each of the other groups, increasing in a linear way. We could also have this influence saturate. And then if you just use the standard mathematical form for saturating a saturating function, you end up with this crossover here, where there's a change in the ordering of who has the most influence. So we can make a fixed order saturating, and then a little like the co-influence functions, we can do a reverse order saturating. Okay, so then the model equations are just the opinion dynamics equations with disease terms added, corresponding to these new compartments. So if we run simulations of the model, magenta here is the final size. And I've ordered these results in the same order as the influence function plot you just saw. So you can see that under these different influence functions, the final size is going down each time. The initial conditions here is that the population was majority non-prophylactic. So they were not expecting disease, were not prepared for it, and had to switch. So when you start with a non-prophylactic majority, that's the red curves, then we obtain final size results like these. If you start with a prophylactic majority, so the population was already prepared and had masks in their drawers and whipped them out right away, then you can see the infection, this black curve, whereas before we have this nice epidemic peak, it's practically invisible. So the population, this prophylactic majority, is able to keep disease spread under control, and final size is much, much lower. And now the difference influence functions are having an effect, but it's smaller. So if we look at more results here, this is plotting results across several different levels of prophylaxis at the beginning. We see final size decreases with the initial level of prophylaxis, but the way it decreases varies. This curve here is no opinion dynamics. So the group that you start out in is the group that you stay in. So whatever your propensity, whatever was your propensity to wear a mask, it has, you know what, that's, I'm really sorry. That's the furnace guy coming to fix my furnace. I'm just going to let him in. I'll be right back. This is, if there are no opinion dynamics. Yeah, I do need the furnace. Thank you I appreciate you understanding. And then this dashed curve is what you get with linear influence. And then all of the saturating influence functions seem to behave the same way in terms of final size. Peak size, similar. Again, the linear influence function is different, but peak size decreases the more prophylaxis you have in the population to start with. Duration is nonlinear. So first, it increases with the initial amount of prophylaxis until it reaches a peak, and then it suddenly drops off. Okay. Now, if we play around with the rates at which these processes are occurring, so the rate, what we did at the top here is we made the opinion dynamics faster. So we kept the disease dynamics, so that's transmission and recovery. We kept those rates the same, but made the opinion dynamics happen faster. When you do that, it's a similar pattern to what I showed you before, just now the effect of the influence functions is much stronger. Down here, we have increased the disease and the opinion dynamics rates, and now the results look quite different. Now there are some cases where the opinion dynamics become so fast that they're counterproductive. Peak size always seems to decrease. It's final size that can change. What's happening with final size is you start getting multiple epidemic waves, which changes the picture a little bit. Duration just goes up in this scenario. If we look at polarization, so what I showed you before was just the initial proportion of the population that's prophylactic, but I assumed that they were divided equally between the moderate and extreme opinions on that side. So now if we look at polarization, now we're talking about those peaks that developed in the spatial model. So if you look in the literature for functions evaluating polarization in the population, we find a number of them in the economics literature, which was interesting. And this is the one we settled on. And notice that it depends only on the opinions at the extremes. It doesn't depend, and we only have, you know, a +2 to -2. So it doesn't depend on the moderates, +1 and -1, only the extremes. So you take the proportion of the population at each extreme, multiply those two. And then we're also interested in the difference. So if you've got a 50-50 split, that's clearly highly polarized. 70-30. Okay, still polarized, but less so. 90-10. Okay, that's starting to become majority. That's not so polarized. So that's what this term is trying to measure. So we take the difference between the proportion at the extremes, square that and subtract it from 1. And when you plot it, you end up with a function like this. So polarization is highest when you've got that even split, and then it gets lower as you get these more higher differences in the split. So we'll start with the proportion prophylactic. So this, any initial point on this red curve is more of them, the population is mostly non-prophylactic, and then on the green, most of the population is prophylactic. And here's what we get. So if we run final size, peak size, and duration, we find that the proportion or the polarization matters, basically. So we're seeing there can be quite big differences in the final size, the peak size, and the duration, depending on how polarized the population is. I'm watching the time. I want to make sure there's questions at the time for questions at the end. So if you're interested in more details, we can talk more later. But in conclusion, what we find is that opinion dynamics can dramatically reduce epidemic size and peak size, and they can also make the epidemic worse. That initial conditions matter. So the proportion that's prophylactic and the degree of polarization also have a big difference. And then the proportion prophylactic is evolving throughout the epidemic as well. So the initial condition matters, but then of course the dynamics throughout matter as well. The rate of adoption of prophylaxis can be too fast and ultimately make the epidemic worse, or too slow, can be behind the epidemic wave and not make any difference. And so what we're finding is that the interactions between opinion dynamics and disease dynamics are complex and can lead to results that wouldn't necessarily be expected if you didn't look at the two together. And so with that, I want to thank you all for listening. Thanks to the MfPH team for inviting me to give this talk. And we have a few minutes for questions.
Thank you very much.